your audience is elsewhere. This is Mary Jane.
Oh, hi, man. Nice to meet you. Everything is perfect going so well. Thank you very much. Everything is really well.
Here's a weird question for you. What's your BMI?
My BMI? I don't know.
Don't ask me that.
So Danny Reese is going to be looking for volunteers.
Oh, he told me about it. Yeah. He sits in my car. That's what he's been doing.
So we need volunteers for a physical activity data collection. The BMI has to be between a certain and a certain.
Oh, okay.
So 18, you should have a BMI of 18 or above.
Yeah, it should be above 18. Yeah.
Okay.
Hopefully.
Yeah.
Can confirm mine is, and way.
Your BMI?
Definitely higher than 18.
Well, sure, so is mine. It's like about twice 18 or private.
No, hopefully not. I don't think it's 20.
Just say, when is,
I mean, that's fine.
1 minute?
Should we just keep it? Reschedule it to like Friday.
No, because I probably won't be here.
Oh.
Well, actually, that's why. No, I'm babysitting next week.
Okay. I think
Alicia,
Yes.
this is Hal. Have you said anything yet? Because I'm not hearing you at all.
No, I haven't said anything yet.
What's
Hal?
that?
Hal? No. Hal?
I shouldn't have to do anything to you, right?
Yeah.
Audio should be automatic.
Last month. So I'm not sure what's going on.
Yeah.
I'm hearing everything you're saying, and I think everyone else is that. I might have something that is that.
Can you communicate with him?
In chat.
Okay. Tell him that everybody else seems to be hearing fine. Although we don't know that either.
I was gonna log in.
Or what? Oh, do that. Thank you.
Are you hearing us now? Al?
Yes.
Oh, goody.
Okay. Thank you. We had a problem here. My fault.
No worries, no worries.
Okay. Thanks.
Are we ready? Already. So, good afternoon, good evening, everybody that's out there listening to us today. We're very pleased to introduce to everybody Adam Kortylewski from the University of Basel. Adam has been visiting the United States whirlwind tour of NIST and Johns Hopkins and Michigan State and now CSAFE. And we're looking forward to his talk. He's going to tell us about shoeprints. Just as a reminder, we have, well, I won't say much at all. The only thing I want to remind everybody is of upcoming events. Our next center-wide webinar will be announced soon, but we're planning on a human subjects topic for the next one. And it's probably going to be planned for late March, early April, but we'll keep you posted. And another reminder is our all hands meeting that's going to happen on June 7, 8, and 9 in Ames, Iowa. More information to be start dripping out soon. In particular, we'll announce when our registration website is open. Please register as soon as you can so that we start getting a reasonable count of participants. As always, we welcome your comments. If you're out there somewhere, please mute yourselves. And if you have questions during the talk, send them, write them down, and Adam will see them on the screen. and the operator is also going to see them. So that's going to make things easier for Adam to respond in a timely way. And of course, at the end of his talk, we're going to have a chance for lots of questions and comments and discussions. So without any further ado, here's Adam.
Thanks for the kind introduction. Can you hear me? Test? Great.
And his slides.
All right, my slides.
There we go.
There we go. All right. Yeah. So hi, I'm Adam. Thanks for having me here. And thanks for giving me the opportunity to talk about my research on a generative approach to shape-based image analysis. Let's first start with introducing the topic of shape-based image analysis. What is this? When I talk about this, I mean the process of inferring the state of the world by analyzing shape patterns in images. Okay, so let's make this a bit more concrete. Let's assume you're a forensic examiner. You enter a crime scene and you see a shoe print on the ground. And the question that you might ask yourself is, which shoe made this impression? Okay, and you know, by assuming you have a catalog of reference prints that you can compare to this impression, this is basically known as a classification problem in computer vision. And shape patterns are really, really useful in answering this question. Okay, or let's go to the next image. You as a human might ask yourself, where is the horse located in this image? Okay, this is known in computer vision as a detection problem. And also the shape pattern, so the shape of the horse, is very useful information for answering this question, yeah, if not mandatory information. All right, next image. You might ask yourself, what time is it by looking at this image? And this is known in computer vision as a pose estimation problem, because you have to detect the whole, the clock, you have to detect its parts, and then you have to study their relative arrangement, spatial configuration. And for all of these three tasks, shape patterns are really useful, if not mandatory, in answering this question. Okay, but not all of the shape patterns that you see in these images, only a subset of them. Namely, only like the relevant ones, those that are relevant to the question that you ask. And finding out which are relevant and which are irrelevant is extremely hard. And what I'm going to present is a framework that is able of doing so for all of these different tasks. And during the talk, I will focus on the Shoeprint classification problem, although I have worked on all of these problems, just because you're probably most interested in this Shoeprint classification thing, and I also spent most of my time at this, working at this problem. So let's have a closer look on what is forensic Shoeprint classification. When I talk about this from a computer vision point of view, this is the setup that I think of. So you have a probe image, and you have a set of so-called reference prints, a whole database of them. And you want to find out which of these prints is most similar to the probe image. All right. In this case, this would be the one that I marked here. And in this case, I want to clarify, I don't think of really identification, Shoeprint identification. It's just you want to know the class of outsole patterns that are most similar. Basically, it's a similarity metric that we will define. And we as humans are really good at this. So we have extremely high classification accuracies. And we're most of the time not aware of what kind of challenges we all have to solve when solving this task. But at that point, when you want to start to teach to the computer what to do, you'll find out. And that's what I want to show on the next slide. I list here a couple of challenges, fundamental challenges that you have to overcome when doing image analysis or computer vision. And this is by no means a complete list. It's just those challenges that I will cover with the approach that I'm presenting later on. All right, so let's start with the first challenging task with or problem, which is occlusion. Okay, so you have a print. You see this on the right, and there is clearly some parts of this print are missing here, at least in those regions where you see these two stripes. And those parts you would see in the reference print that you compare. And somehow your vision system has to realize that and has to compensate this, to account for this. So this is really not an easy task, although we do this like very fast and are completely unaware of this, basically, in our everyday lives. Then very often we also have structured background clutter. So structured information in the background that is not useful for answering the question that we are asking. And what is interesting about this picture, for untrained humans, it is even difficult to find out what is now the useful information, what is irrelevant. And for me, as a non-forensic expert, but with a bit of experience, I would say at least these two regions might be useful. So here we can see that this task is really not easy to separate the relevant from the irrelevant information. In fact, it's highly difficult. Then we'll have localization. What I mean by that is basically patterns that you want to compare. They are rotated, translated, and scaled relative to each other, so you have to account for this. Then what we also see a lot in Shoeprint images, but not only in Shoeprint images, are local deformations. And I visualized this here with these two images. What you should look at are these two ellipses. And in the reference prints, you see these knobs. And and what you should also see in the probe print is that these knobs have deformed. And this happens, I think, because you commit a crime, you don't just walk away, probably you run away, yeah? And that's, the force that acts upon like touching the ground when running deforms these knobs. This leads to this local deformation. And you also have to account for, you have to realize that somehow, you have to find this out and account for this. Which is also highly difficult. Yeah? And then we'll have large non-rigid deformations. And this should be illustrated in this image. What you see is in the background in gray is the probe image. And I overlaid the reference print over the probe image in orange. And I aligned them so that they are, so I rigidly aligned them in the toe region. So in the toe region, they match fairly well, but in the heel, you see there is large deformation. Probably also, some force that worked on the outsole, that acted on the outsole upon running. That's I don't know, I don't know this hidden process, but somehow this occurred. And we have to separately account for these local and large non-rigid deformations. We'll see why later on. And the last thing that I will talk about is appearance change. And what I mean here by appearance change is basically contrast variation. So what you see in the toe region, the contrast is in at some places it's much lower than, for example, in the heel region. So the contrast between foreground and background might be different in different areas of the shoe. And a simple Euclidean distance won't solve the problem. You have to locally account for this. And what I'm going to present is a framework that handles or solves basically all of these tasks at once in a joint manner. Okay. Now, let's have a look at the image analysis framework that I'm going to present. I'm going to introduce this on 3 different scales. One very abstract introduction, then I will talk about these boxes in a bit more detail, and then we're going to go in full detail. All right, so the main elements of the framework that I'm going to present are the training data. So you will have some kind of training images that you will learn something from. Then we will have a generative image model that is parameterized by these parameters theta. And by fixing this parameter, we will be able to synthesize a new image. Okay, so we will be able to generate new images. And at runtime, we will have a new probe print I prime. And what we will do is to change these parameters theta such that the synthesized image is as close to the probe image as possible. So we will try to reconstruct this probe image. And this is called in computer vision analysis by synthesis, because when we are able to find these optimal parameters theta, we will be able to interpret them and then to find out about the states of the world that we want to infer or to know about. For example, what shoeprint is this? What orientation does it have? All of that. Okay. And how I will, so in the next step, what we'll do after learning this generative model, we will basically learn separate generative models for separate reference prints. So at training time, we'll have, let's say, a whole database of reference prints. We will learn a generative model for each of these. And then we'll also do the inference for each of these models. And like the reconstruction score that we will obtain later on will serve as the similarity measure. Okay, so that's the overall pipeline. Let's have a look in a bit more detail. How can these training images look like? So during the talk, I will basically use single shape masks, meaning you have black on white, the shape, like separated the shape and the background. Okay, so this could be these reference prints, as I showed already. This could be like horse masks, whatever. This could also be like these the reference prints of fingerprints. I mean, they are basically, you have on black the pattern and the background is a bit grayish noise. So one single image, black on white. Or what you could also use is a set of natural images that somehow depict the shape that you want to model. This is much more difficult. And I won't talk about this in this talk, but I have also worked on that. All right, so we'll use a single shape mask during this talk. And then we'll learn the generative model. And there is like one key trick that we will apply. And this is that we will assume a certain image formation process. Okay, so we will split so we will do a basis decomposition of the image. And while doing so, after doing so, we will have split the image into 3 parts, namely what I show here as C, B, and U. Okay, one of these parts will be responsible for the shape and shape variations. One will be responsible for the appearance, meaning like real pixel values, intensities at the pixel level. And one will be responsible for the background. This is really, it's a simple, but it's basically the key trick. So we will learn this from the input image, from the training image. And what we're going to do next is that we will impose a statistical distribution on all of these parameters, on the B, the C, and the U. And by doing so, we can later on vary these parameters. And in this way, we will be able to generate new images. Okay? So part of these distributions will be learned from the data. We will learn as much as we can from the data, and the rest we will like use our expert knowledge for modeling. Okay? So what I note here as P of B is the distribution on the parameter B, and this will later on enable us or make possible to account for local deformations, for large non-rigid deformations, and also for global deformations. okay? Then we'll have the distribution on the C parameter. This will let us account for contrast variation. And we'll also impose one on the U. This will later on lead to structured, the ability to model structured background, basically. All right. Now, so the B, the C, and the U are our parameters that I denote here by theta. And the interplay between the foreground and the background will enable us, will make possible to account for occlusions, yeah, which is one of the challenges, which is like one of the main challenges that we have to account for. So as you see, we will have all of these challenges are part of the model that we designed here. And at runtime, we will infer all of the parameters globally at once in one pass. So there is no iterative process also going on. All right, that's the setup. Let's have a really detailed look now on these boxes that I showed you. And we'll start with the image formation process, okay? So the training image is here, this reference print. And what we'll do is we will decompose it into a linear combination of basis vectors, BI, and plus a residual image. So we will project this onto this basis BI. And you can think of this basis of being some kinds of filters. Could be Gabor filters, could be any wavelet, whatever you might think of. I will, during the talk, I will use these Gabor filters as example, but it turns out that tuning these filters and learning them from the data helps a lot. But for the sake of simplicity, I'll stick to these Gabor filters for the rest of the talk. And I will depict them as these orange blob-like structures, okay? Just because it's much more illustrative. You can see them much better on the slides, all right? So we're gonna now project this image onto the spaces, and this will look like this, okay? So we'll have now different filters in different orientations at different positions in the image. That's basically what I've done here, all right? And all of those parts of the image that have not been explained by filters will be later on explained by the residual image here. All right. Now these filters have parameters, beta, and they are parameterized relative to the center of the image. So we'll have the center of the image, which is beta superscript 0, which is just the center, so the center position and center orientation of the training print. And then we will encode each of these filters relative to the center. So that when we rotate the center, all of the filters will be rotating. So we'll have here the X, which is the relative position, and delta alpha, which is the relative orientation. And we will collect them into this set R. Okay, and this is now responsible for the shape of the shoe. Then we'll have the filter coefficients, CI, and the residual image U. So we have now split the image into the filter coefficients, which can like generate images later on. We'll have the shape. By varying the filter positions, we will be able to deform the print. And then we'll have the residual image, and we'll come to that later on. All right, now let's impose a statistical distribution on these filter positions, which is now the P of R, right? And we'll start by letting these filters move locally a bit. So they can move plus minus, let's say, 2 pixels and plus minus 5 degrees. All right, this is what I denote here with this uniform distribution. So they can move independently of each other according to a uniform distribution in a range of plus minus something. Okay, and this looks like this. So this is the projection. And now when you sample from this distribution, what you see is that they can jiggle around a bit. All right. This is now later on in the inference. This will enable us to compensate this local deformation, which is great. This is known as the active basis model. So you have a basis, you project your data onto this basis, and then you let the basis also perturb locally. All right. So we can now account for local deformations. Now, what we will also impose a statistical distribution on these beta superscript 0, which is basically a uniform distribution over the position and the orientation. So the shoeprint is basically allowed to change its position and orientation as it wants. We have no additional information here. And now we can stick them together, use these independence assumption, and this will result in this model here. Okay, so this is now our deformation model. We have our distribution, our prior on the beta 0, on the center position and orientation. And then relative to this, we have our jiggling conditional. All right. Now there's one issue with this model, namely that when you want to account for these large non-rigid deformations, these filters have to move a lot, okay? And as we use this independence assumption, this leads to a loss of structure in the data. So when you let them jiggle a lot independently, this is what I show here. This is a sample from a distribution that is allowed to move plus minus 10 pixels instead of plus minus 2 pixels, as I show here. And what you see is that clearly the structure gets somehow lost. So there is a bit left, but there is a lot of information is lost. And what is even worse is that at some point, filters can switch their position, which is a very unnatural deformation, basically. Okay, so you don't want your model to do this. I mean, you could also think of what must happen to an outsole that, you know, parts switch their position. Is like totally, it's unnatural, and you want to avoid this. And the idea, it's like we had one idea for avoiding this, namely that filters, if they want to move far, they have to move in groups. Okay, so like coupling them locally. That's the idea. And then there is like lots of questions popping out, namely like, what is the size of groups? How many how many groups? How far can they move? And this is basically what we have done here in this paper. The basic principle is you cluster these filters into higher order parts. This is what I show here. So you have the reference. You have the reference encoded by just one filter in different orientations and positions. And now based on this encoding, you look for spatial occurrences of filter that, you know, that occur very frequently. So you look for groups that occur very frequently. This is what the algorithm then learned on the next level. So what I say is you cluster two filters that have a relative configuration that you see very often in the data. And the algorithm said, all right, I found this one here, which is basically two filters next to each other in more or less the same orientation. And this red one here, which is saying I have two filters parallel to each other. Okay, and when you look for these parts in the original data, you will find them in these positions. What you see is that basically the red one encodes the parallel lines, and the blue one tries to encode the straight lines, more or less, or the slightly curved lines. All right, and then you'll cluster these again. So on the next higher level, these two here have to be clustered into some relative spatial configuration that they occur frequently. And what happened is that, for example, this green one here is composed of two of the red ones next to each other, and so on. You can go on here in a hierarchical manner. It's just the constraint is it's always two parts from the layer before, which is called hierarchical compositional clustering. All right, so we get higher and bigger parts, and at some point, you know, the algorithm stops because you parameterized it in that way, and then you have a whole dictionary of parts, which is not yet a holistic model. So you go top down and collect all of those parts that do not overlap. So the not overlapping is an important feature because it must be a basis, yeah? They should be independent of each other. And this will then result in this final model here. And what you can now do is let these bigger parts move more. If the data says so, they can move, all right? But only together. That's the constraint, right? And in this way, you can somehow compensate these larger deformations, yeah? Without having this independence assumption. This is one way of doing this. There is many other ways. This approach has its problems, of course, yeah? But you know, we can now account for these large deformations, at least a bit. All right, so we're now set with the deformations. We have local deformations, we have large non-rigid deformations, we have this global alignment. What about the contrast variation? And we will account for this by letting these filter coefficients change a bit. Okay, so we'll define a distribution on the filter coefficients, and this distribution looks like this. You can hand design this, you can learn this from data or whatever. This distribution says large, so what you see on the x-axis is the filter coefficient, and on the y-axis you see its likelihood, basically. It stands t. So what it says is that large filter coefficients are very likely and low filter coefficients are very unlikely. And this is what you would expect at, you know, at these edge-like positions. And each filter is able to emit one of these coefficients independently of the rest. It's an important assumption which makes life easier during inference. All right, and the final model will look like this. So depending on the filter position, so for each filter, independently, which is here, the factorization, filter coefficients can be emitted according to this distribution that I showed before. All right, so you could sample from this, and you would see that the contrast can vary in the image. Now, let's go to the final model, which is the one for the background. And the background we'll use a trick here, will be decomposed in the same way as the foreground. Also as like a linear combination of these filters. Just not at those positions where the foreground model is active. This is what this sum here means. So everywhere where there is no foreground filter, we'll have a background filter. In some position, some orientation, and some coefficient. And now the trick is the background coefficients, they follow a different distribution. And as the reference print has basically no background, we'll have to learn this distribution from somewhere. And what we did is just we collected these textures that happen to occur more or less frequently on Shoeprints, and we'll just estimated the histogram of filter coefficients, which is what you see here. And the interesting thing is that now what this distribution says is that in the background, low coefficients are very likely and larger coefficients are more unlikely. Although you might have strong edges in the background, it's not very typical. Yeah? This is just one assumption. Yeah, I mean, it might be. Yeah, you can choose different models here. It's just what we have done, yeah, in this case. All right, so we have one distribution for the foreground where the high filter coefficients are likely, and one for the background where the lower coefficients are more likely. And again, at each position, these coefficients can be emitted independently. All right. Now we can use these two distributions to account for occlusion in the following way. Namely, we'll extend the model in a way, so we'll introduce a new variable, zi, and the zi is binary, so it can be 1 or 0. And what this formula basically says is that if if a coefficient is more likely to, has a higher likelihood under the foreground appearance model than on the background appearance model, you can switch this z. Okay, so if the z is 1, this term is active. And if it's 0, then the background term is active. And during runtime, you'll observe a filter coefficient. You check which distribution is bigger, and then you'll set the variable z, right? And so the main effect of this is that during inference, when you look at data, you don't know which parts are occluded. You have your foreground model, and it tries to explain really, really small filter coefficients. And as you have seen, the likelihood of small coefficients is super low. And this might really disturb the result, distort the result. So this is one way of more robustly fitting this model. All right, let's have a look at the inference process. So we'll formulate this in a Bayesian setup. We'll say the posterior of the parameters theta, given a new probe image that we have not seen before, can be factorized into a prior and the likelihood, and we'll split the image into foreground and background, as we have done in, like, this is our image formation assumption, and then we can plug in the models that we have developed so far, which will result in this formula. Okay, so we have here the background, we have here the prior on the orientation, on the center orientation and position, the relative position of the filters, and then the coefficient that they emit. And if we want to optimize that, we can do this in a bottom-up manner. Okay, so because of these nice independence assumptions that we made, we can use dynamic programming to optimize this. So this is a tree-like structure. We can first optimize for these parameters, find the optimal one. We'll go one stage higher, find the optimal one, and then we'll find the beta 0 that is optimal. So we can really optimize each branch independently of the rest, which is basic. This is the message that should be made by this slide. And we can do this, it's not so important, basically by convolutions, which can be done very efficiently in modern computers. Now, if we use these hierarchical models, what will happen to this tree is that basically we will have intermediate layers, but still we'll have this independence assumption. So we will be optimizing all of these these structures here independently, and then we'll be optimizing this part of the tree and then this part, like in parallel, and then we'll go to the next layer. So we can do bottom-up hierarchical inference basically with convolutions. That's the message that should be transported by these slides. So just very efficient. It's a global solution. It's the global optimal solution of our model, which is very nice. All right, so at runtime, we'll get a probe. Let's say we have, somebody gives us the correct reference. We don't have this in the standard setup, but let's say we want to compare these two. Okay, so how similar is this to that one? What we'll do is we learn the model from our reference print, as I said before. We'll get our parameters R, C, and U, and then we will search for the optimal posterior given the print and the model that we learned with this bottom-up hierarchical approach. And the result will look like this. So what I depict here is basically the individual variables, the map result for the individual variables. So we'll have the probe here. Then next to it, I visualized the optimal beta knot. So the optimal position and orientation of the ref. So I use the reference print to show this. Yeah. So what you see is that basically the reference print and the probe, they are fairly well aligned. Then the Zs, these are the occlusion variables. So I'll try to illustrate this in the middle picture. What you see is that the filter model at the optimal position, and in red are the active filters. So those for which the coefficient is higher than in the background model, and in blue, all of those that have been deactivated. So the algorithm is really capable of finding those relevant shape information, which is really nice. This is a really nice result. So basically what the human would say is like the shape information that is relevant, namely over here at the top, and yeah, in some positions here, the algorithm is somehow capable to extract that. It's not perfect, but it's, for example, it's not distorted by these strong edges, yeah, which is interesting. Yeah? And then, yeah, I'll show here the foreground reconstruction, basically. So the red filters and their optimal coefficients, and here the background. What you see that like in the background, also the structures, they have been fairly well reconstructed. Although it's, of course, it's not a pixel-wise perfect reconstruction. It's just, you know, you have the filters and you assume they can reconstruct the image well. And this is the best you can do. So given a probe and the reference, we can do this, which is nice. But unfortunately, at runtime, we don't know what is the right reference, right? So what we'll do, straightforward, we learn this generative model for each of those prints, and then at runtime we will perform the inference for each of those. So we'll have 1,200 generative models that we will optimize. We'll get their posteriors, and then we will sort them according to their posterior value. And the result looks like this. So the curve shows this, it's a cumulative match curve, and it basically illustrates how, like, you have the sorted list. How likely is it that under the first, X%, you will be able to find the correct reference? What you see here is, like, let's use on the x-axis the value 5%. So you look at the first 5% of the sorted list, which are basically 60 prints. So what is the likelihood of, what is the chance of finding in the top 60 the correct reference? And on the bottom, you see the results that we re-implemented that have been done before. Then in the red, you see the result that I published a couple of years ago. It was my first approach. Yeah? They are all feature-based. They are not generative. Yeah? So discriminative models. You calculate some feature, you compare that, that's it. Okay? And what you see is that basically at 5%, this red curve has a chance of 30% to find the correct one. And by using our approach, tuning the filters a bit, there is a huge improvement. Okay, so at 5%, it's basically the chances more or less 70% of finding the correct reference. We'll have 300 probes here, and this is quite good. But as you see, it's not yet the solution. Now, let's assume you'll increase the database to 20,000. You won't like to search through the first 5% of these 20,000. Yeah? So there is still work to do. What is nice is that we have now a really nice framework where we can, each box can be optimized. Yeah? It's not the optimal solution. It's just visualization and of the problems, all of the problems that you have to solve. So these are cherry-picked retrieval results. So what I show at the top is a double print, like 2 prints overlaid. This might be a problem for some approaches, but what our approach is capable of is basically, so what you see is the probe and then the top 6 result of this sorted list. So the first one is the correct one, of course. But what you also see is that all of the others, they are very similar, which is good. It's always good if the machine similarity somehow resembles human similarity. And and the scores are likelihood ratios, namely the posterior that we calculated over modeling this image only by the background model, only by the P of U. So we have the foreground against the background in the likelihood ratio. So we can handle double prints if there is like enough information outside. That's basically the constraint. Yeah. And what you see here is one problem, namely, you see the pattern, like the probe pattern is very latent. So the coefficients, they are not so high, they're, you know, directly at the border, but and they're a strong edge, yeah, where the coefficients are very high and they're likely foreground. And what the algorithm, when you look at the results, it really tries to fit the strong edge. So when the pattern is latent in the background, like it prefers strong edges. Yeah? So you find the correct print is here, the fourth one, but you know it's not really the result that we want. All right, so these are some problems. I'll very quickly rush over how to learn these shape models from a couple of images where you don't have like the shape supervised annotated. So we'll basically use the same clustering approach. We'll have a bottom-up clustering of these filters and the top-down composition, and we are able to learn these shape models from images, which is quite nice. We can learn this for different class of images. You see this here for bikes, for horses, and on the right, the models. They're not perfect, but it's fairly nice. Nobody has annotated them. We just know there are some horses in these images. And that's basically it, okay? So what I've shown is a generative framework for the analysis of shape patterns in images, that these patterns can be occluded, deformed, they can change their appearance. We have structured background. We'll have significantly increased the Shoeprint retrieval performance. And what I think is the best about all of this is that we have now a model, we have separated all of the parts basically, and we can now start to improve in each of these boxes. So this is basically is just the beginning of what will happen. All right, that's it. Thank you.
Ask whether people have questions.
Any questions?
Okay. So the training data that you use for your algorithm. So I'm guessing that the training images that you have to be very high quality images. Or they can be any images that you can get in real life example.
Okay, so the question is what kind of training data? And I don't know what you mean by high quality, but
like when you take a shoe, new shoe, and you take the print.
Yeah. So I suppose that they're like, I assume they're black and white more or less, but I mean, so what you see here is, this is basically the training data, and you know, they are more or less black and white. I mean, they're used, they're not new shoes. So you have accidentals and all of that stuff in there. It's like, I mean, the better the quality, the better the result. But you know, you take what you get. Yeah? So they can be used. There are, I mean, like, I don't know if you see this, but here, for example, there is like clear structure that, you know, is not present anymore. And this is an issue. Yeah, you might have missing information in your training data that you see in the probe image. So how do you handle that? It's not.
So a particular shoe you don't have in a reference print.
Yeah. When I don't have the reference print, then you know.
Does it like falsely detect something else, or
there is no? So that's the trick. There is no detection happening. You just take what you have, you sort it, and that's it. You never say, you know, this is the threshold where there is a detection. Yeah, that's a a really important question, and yeah.
So you just try to get as many prints as you can.
Yeah. So So what you do is you gather so many. Yeah. You get so many prints as you get, and you hope that the right is in.
Okay.
And if the algorithm is good, you search, you look through the top 20, and if it's not in there, then then the chance is very high that you don't have the right shoe, which is also important information.
So I have a question for
Yeah.
you. So you showed, for example, for this retrieval, all the retrievals, you showed this likelihood ratio values.
Yeah.
And in the first case, you had that the larger likelihood ratio corresponded to the actual true match, if you will. But the other likelihood ratios are pretty high too. And so have you, I mean, I'm thinking of these sort of like a score, right?
Yeah.
So you could actually compute, so you could look at all the score values that you get for true matches. So if you have a true match, you get 184, 591,
yeah,
and so on and so forth. And then compare the distribution of the scores among known matches.
Oh yeah.
With the distribution of the scores among known matches.
Yeah, this is what I didn't show here. Yeah, but so this is a cumulative match curve. But what you could also draw is an ROC curve, where you basically you make a decision, this is a match or not, and vary the threshold, the score. Yeah.
Yes.
And it would be interesting to have this here. Yeah, but I didn't. Yeah.
Okay.
Yeah. Yeah.
And so how do you resolve the issue that if I look at those two, the scales are very different, right? So you have 300. So you have 1800 in the top, and
so
it's the same scale, I guess.
The scales are very different. I mean, so it's like, so it happens because the edges here, they are very strong. That's why they get, high likelihood in the foreground model. That's why the likelihood ratio is very high. Whereas here, this pattern is very latent. The coefficients, they are barely, they are somewhere in the middle. Yeah, so the likelihood is not so high. That's why the likelihood ratio is so low. So this is just, this is just one. So what you could do is you go bottom up, calculate the optimal positioning, and then you could change the foreground and background models. You could go top down and say, okay, now I look for parts that I maybe missed. So at some point, you'll make a decision in the bottom-up process, this part is present or not, and continue going up. But once you have the optimal position, you can go down, change your thresholds, which is basically changing the background model, and pick up stuff that you missed. So that might be interesting. I mean, the difference between the scores is just because the latent patterns that they're like this. The way I designed the model, they are just more unlikely. Any more questions? If not, then thank you.
Oh, sure. Thank you, everybody, for joining us today. There's still time to ask questions if you want to. Did we ask Adam whether we've recorded you? Is that okay?
Oh!
Better late than never. We can always erase the recording.
It's okay. No, it's all right.
Okay.
I'm okay with that.
So this could be retrieved afterwards for somebody that wants to watch it.
Oh, great! I put it on my webpage. Yeah.
There you go. Yeah. Okay. So if anybody would like to see some of the slides or talk to Adam, we'll post his contact information.
Great. Yeah.
Thank you very much, and we'll see you next time.
Yeah.
Never worked with English.
Okay. Is the chain. You can. Yeah, I always think of it as a matrix.
It's a matrix. Okay.